Okay guys, so this lesson is the progression from our first two lessons. Our first two lessons were obviously looking at trying to find the slope of a particular function at any point, and we ended up saying, well, let's try and get a derivative function, which means that we can input any value and find out the slope at any value. So that whole process that we worked through in the last few lessons was called first principles. And that's because it's based on the first principles of, trying to find the slope from 2 points and reducing them using the ideas of limits. So what we're trying to do now is shortcut that, because that gets very tiring very quick. It's a long way of going around. So we're going to try and find basically a shortcut, a bit of a cheats method. And we're going to try and just observe what happens from some fairly simple functions to try and make a bit of a shortcut. And from that, try and make up a general rule. So in the first little table there, I've made this table just here, which I'd like you to try and fill in using first principles. Now, if you're feeling like you already know how to do this, please don't. Do it with first principles. And the reason why I say that is because in the test, in the exam, you are required to use first principles to be able to do this. And if you skip that process, you'll be pretty rusty at it by the time the exam comes around. So spend some time, going through these again, doing the first principles. This is actually about a bit of brain training. So do the first principles, find out the results for these, and then we'll continue on with the video. So pause the video now, right now. If you haven't paused it yet, pause it. Go and pause it. Okay, I'm assuming you paused, and welcome back. So I'm just going to fill in these now. I'm hoping that you've paused it and filled them in. If you haven't, go back and do it. Don't be lazy. Okay, so for the first one, you should have got the derivative as 1. Second one, you should have got the derivative as 5. Third one, you should have got 2x. Third one, you should have got something like minus 1 on x. And that could look, x squared. That could look a few different ways, depending on how you simplify that. And the last one is going to be minus, sorry, my pen's not working, minus 2 on x cubed. Okay, so just check that that's what you got. You may have got something like this. So this is, we could write this in another way, couldn't we? We could say minus x minus 2. This is using index laws and the fact that any index written on the bottom, on the denominator, if we write in the numerator position, we have to change the sign. So the same with this one over here. This could be minus 2x to the power of minus 3. Okay, so we're trying to find a general rule just by observation. So we're trying to look at, essentially we're looking at this guy here, and we're trying to come up with a rule that makes sense. So if we've got some function that has some number a, and that could be 1, but it could be 5, like it was up here, x to the power of n, and n really, we want to be able to be anything. At the moment, we've got, the power of 1, the power of 1, the power of 2, minus 1, minus 2, and we've found some patterns. So have a think now, just pause the video again, and try and think about coming up with a general rule, okay? Okay, welcome back. Thanks for pausing. If you're still struggling with the pausing, I'll just keep buffering this with some chit-chat. Excellent, well done. Hopefully you're on track. Okay, so as a general rule, if we're looking at this, we could try and think about what's happening with the powers here. So I'm just going to add a power onto here and say, well, this is actually, oh, hang on, don't want to do that. This is actually to the power of 1, isn't it? And this here is actually the power of 0. And this one here is to the power of 0. So if we think about what happens, this is 1, and this is 1, what happens to the power? The power is always going from 1 to 0, 1 to 0, from 2 to 1, from minus 1 to minus 2, from minus 2 to minus 3. So this number down here, n, is always dropping by 1, isn't it? So let's start with that. So x to the power of n minus 1. What happens to that though? So the number down in the front here, so 1 here, we notice is actually found there. And there's a 1 there, and it's kind of represented with 5 times 1. The 5 just carries on. So the 5's there, and the 1 from that index multiplies by the 5. You end up with 5. If we look at this one, the 2 is represented there. So the 2's there, and the 2's there. So not only does the power drop by 1, but also the power seems to come down into this position before it drops. Okay, so you'll notice if we check that on the bottom one here, we had a -2, and there's the -2. And then, there's it there as well. And then we drop the power by 1. Okay, so as a general rule, this part of it, let's just get a red. This part of it goes to what I've got there now. The extension of that is that, well, I have an A, and A is just any value, okay, any number. And A just goes along for the party. So an A just sits there in the front. Doesn't do anything, it just sits there. And you can see that from the 5, right? The 5 was there, and the 5 ends up just out in front. Okay, so let's have a look at how this might work for another example. So if we have our general rule now, if we say if f of x is equal to 3x to the power of 5, then to process that is actually a pretty straightforward episode. The first thing I want to do is I want to think about bringing this down and multiplying whatever's out the front. If there's nothing out the front, there's actually a 1 there. So I'd multiply 5 by 1. But if there's something there, I've got to do 3. So 3 times 5 times 5, x to the power of 4. Okay, and that came from that -1. Okay. So if I complete that, I get 15x to the power of 4. Okay. And you could confirm that using first principles. It'd be an absolute dog, because it means you'd have to expand some sort of power of 5, which is disgusting. I think Ryan did that the other day. If you did the last question, then you would have had to do that. So it's a much quicker step. You could pretty much go from that straight to that in one go. Let's look at another example. If f of x is equal to, so this time I'm going to have 0.2 on x to the power of 6. All right. So the first thing we want to do is get it into this form that we see for our general form, in the form of ax to the power of n. And this is just that. It's ax to the power of n, where a, if we rewrite this, is 0.2, x, and n is the power of -6. So for these, we want to try and think about it in terms of a non-fractional or non-denominator power. So we want to write it like that using our index laws. Once we've got it like that, look, it's pretty straightforward, guys. So the derivative is then given by, okay, the 6 comes down and multiplies. So I've got 0.2 multiplied by -6, just be careful of the -6, the minus got to come with it, x, and then I drop a power on there, so I've got to subtract 1, so you got to be careful. It's going to go to 7, it's not going to go up to 5, because that would be adding 1. Okay, and then I can just simplify this. So this is going to be 0.1, oops, sorry, let's try that again. 1.2 x to the power of -7. Okay, I could be done. If I wanted to be fancy, I could rewrite that and say, well, that's the same as 1.2 x to the power of 7. But I don't really care, right? I wouldn't worry about that. That's called simplifying. For the moment, we actually don't really care if it's simplified or not. This is perfect. So I'll leave it like that. Okay. Let's just look at one more example, and this example is going to combine a few. So if f of x is equal to 6x plus 3x squared, take 9x cubed. Okay, so this looks a lot more complicated, but one of the rules of differentiation is that you can deal with each term individually, and find out the derivative of each. So all we need to do for this is find out the derivative of each component, as you would expect, really. So we'll find out the derivative of that. So remember, to start off with, this is the power of 1. So I'm bringing the 1 and multiplying it by 6, which is just 6, x, and then I've got to drop 1 by 1 power, which is 0. So effectively, whenever you've got something linear, and what I mean by linear is it's not a power of 2 or 3 or 4, it's a power of 1, which means it's a straight line, hence linear. Whenever I have a linear term, it's always going to be just the value at the front. Okay, so that'll always just cancel out. The x disappears. Okay, what about the 3x squared? So the 3 multiplies by the 2. 2 comes down, 6, x, and drop a power to 1. Obviously, I wouldn't write the 1. I'd just write 6x. Okay, what about the 9? So I get 9 times 3, 27x squared. Okay, the negative just goes with it. Right, and I'm done. Right, so even though something looks more complicated like that, you just deal with each individual term one by one. Okay, so hopefully this is what you've done in year 11, and this is sort of revisionary, but this is, I suppose, going back to the start, this is actually a pretty big finding. Like, don't underestimate the maths that went into trying to discover what seems to be quite a simple general rule. Took a lot of mathematicians, a lot of work to try and get to this point. So it is a big thing. And to start off with, we're just talking about fairly simple functions that we just want to try and get used to. So I'm going to upload some problems for you to just have some practice with this. If you're finding it really straightforward, then I would just select sampling some and then moving on. If you're finding it a little bit challenging, then I would recommend trying to do as many as you can. Reason for that is this is really going to form the basis for this whole topic. You know, if you're struggling with this, then you will struggle the whole way through. If you really get a good handle of this, that'll make your life a whole lot easier. Okay, so put the hard work in now. Spend some time trying to get as much of this so that it just becomes automatic. Okay, you almost don't want to think when you see these. You just start writing stuff out. Okay.